My name is Dongbai, and the title of my talk today is Scaling Law of Quantum Entanglement in Nuclear Shear Model. And I come from Hohai University in Nanjing, China. And
Can you put the microphone?
So we speak louder. Okay.
This room has problems. If we turn on the, if we connect the microphone, then Zoom people cannot hear him at all. There's some interference. So you're welcome to sit at the front. You know, we have a lot.
And my city in Nanjing literally means capital in the south. Although not the capital at present, it was the capital of China in history for many times. And my university is called Hohai University. Hohai, these two words literally means river and sea. So you start to get the feeling that our university is good at water science and water engineering. Actually, it is best at hydraulic engineering, building dams and digging tunnels. It helps to build the Jinping Dam, and which is the tallest dam in the world. In order to get more electric power from the dam, they dig several long tunnels in the Jinping Mountain. This mountain is so high that some smart people in China realize that these tunnels are perfect place for dark matter, nuclear astrophysics, and neutrinos, double beta decay, and some other stuffs. Nevertheless, it's fair to say that our university is not the conventional place to study nuclear physics in China. So when I get my position 3 years ago, I think this will be a great chance to explore some unconventional topics in nuclear physics, such as entanglement in atomic nuclei. Entanglement is a classically forbidden form of correlation shared by separate local systems. In order to figure out what is entanglement, one has to first figure out what is not entanglement. Mathematically, an unentangled state is simply the product state. Let's say this state has n parts. If the total wave function can be written into the direct product of the n parts, then this is an unentangled state. Then the entangled state is the state that is not unentangled. In other words, this state cannot be put into the direct product form of n parts. So by definition, in order to have an entangled state, one should have at least two parts. And for each part, the simplest system could be qubits. The qubits are just a fancy name for two-level quantum systems whose dimension of the Hilbert space is equal to 2, and one can label its basis vectors as a 0 and 1 state. The qubits can be mapped into a sphere. So in literature, one can draw qubits as spheres. So the simplest entangled state should be the entangled states of 2 qubits. And the most famous 2-qubit entangled states are the Bell states. There are 4 Bell states, and in the slides I show one of them. You can prove easily that these states cannot be put into the direct product form. In other words, this state is entangled. Okay. In general, we can have more complicated entangled states other than the 2-qubit entangled states. So we can divide a general model space into 2 parts, the part A and part B. So we can start to think about the entanglement between these two. Entanglement between A and B, one can use the so-called Rayleigh entanglement entropy. And the definition is shown in the middle of the slide. And the key building block is a reduced density matrix for part A, or equivalently part B. And there's a free parameter alpha in the definition, and you can choose arbitrary in principle, you can choose many different values of alpha in the Rayleigh entanglement entropy. And the Rayleigh entanglement entropy has an important property, that is, it is symmetric between the part A and part B. And we will see its power in the following slide. And also, when alpha equals to 2, we get a special case of the Rayleigh entropy, that is a second Rayleigh entropy, or we can call it as a Rayleigh 2 entropy. And the advantage of this Rayleigh 2 entropy is that the first, it is slightly easier to compute the Rayleigh 2 entropy numerically. And the second, and what is more important is that this Rayleigh 2 entropy can be measured in experiments, for example, in some ultra-cold atomic systems. The key magic of the Rayleigh 2 entropy is that its key building block is the so-called purity. And it is this purity that can be measured in ultra-cold atomic systems. So in the following, I will mainly focus on the Rayleigh 2 entropy. After figuring out how to quantify the entanglement between part A and part B, we can start to think about how the Rayleigh 2 entropy scales with the size of the part A. There are two typical scaling behavior, and the first is called the error law. That is, the entropy scales. That is, entropy is proportional to the area of the part A. And this kind of scaling behavior can be found in the ground state of lattice systems with short-range interactions. And the second typical behavior is called the volume law, where the entropy scales, where the entropy is proportional to the volume. And this can be found in, for example, the random states in the Hilbert space. And this is first figured out by Don Page in 1993. And he showed that when you pick out a random state in the Hilbert space and calculate its entanglement, you will generally get some volume law behavior. And the second place to find the volume law behavior is a highly excited eigenstate. And this is related to the very famous eigenstate summarization hypothesis, which basically say that a typical eigenstates of non-integrable systems are self-summarized. Therefore, the reduced density matrix of rho 1 is approximately equal to a reduced density matrix of a thermal system. And so that means the entanglement entropy is approximately equal to the thermal entropy. And we all know that the thermal entropy is proportional to the volumes. So is the entanglement entropy. And this this has been verified experimentally by the Harvard group in 2016. And I have to say that the volume law does not. The volume law in quantum system does not hold for arbitrary large subsystems. And when for subsystems whose volume is smaller than the half volume, we have the volume law here. We have the volume law. And when the subsystem, let's say the part A, exceeds the half volume, then the quantum correlations will take over and bend down the scaling behavior. And this is the difference between the entanglement entropy and the thermal entropy. And this bend down behavior is also consistent with the symmetric properties of the entanglement entropy. And as I said just now, the entanglement entropy is symmetric to part A and part B. So we can see this symmetric behavior with respect to the half volume. And 2 years ago, there are two pioneering works on the scaling behavior of quantum entanglement in atomic nuclei. And the first is done by the MIT group. They do their analysis based on the generalized context theory for the short-range correlations. And the second is done by the Tennessee group, and they do their analysis based on cluster theory. And in their work, they divide the Hilbert space they divide the Hilbert space into the particle space and the whole space and studied the entanglement between these two spaces. And it is interesting to know that although they divide the Hilbert space in different ways, both groups obtain some kind of volume laws for the nuclear entanglement in ground states. So my motivation is to carry out a new study within the nuclear shell model, which is a standard model for atomic nuclei, and covering both ground states and excited states. And I also want to do the analysis in a way that is more standard to quantum information science. So in nuclear shell model, the Hamiltonian can be divided into two parts. The first is a mean field part.
Mike, can I ask one question, please?
Okay.
Just I want to know, please, what is the volume and the area of what exactly?
I mean,
Could you repeat, please? I'm trying to
Yes,
raise
sure.
the voice. Could you repeat your question, please?
Yeah, sure. I want just to understand the volume and the area of what exactly, Bombay.
okay. The volume here means the scaling is the scaling will be proportional to the number of the number of particles. The number of particles in let's say the part A. And I admit that it's not easy to define area law in atomic nuclei, but this area law can be defined in lattice system, where in the real space you can have some you can divide the lattice into two parts, part A and part B, and it's safe to talk about the surface. It's safe to talk about the area of the surface that separate the part A and part B. So in atomic nuclei, for example, in nuclear shell model, I will mainly talk about the volume law. That means the scaling is proportional to the number of particles, maybe I can. I will discuss this issue in later slides. Can we move on? Okay. And in nuclear shell model, we have the two contributions to the Hamiltonian. The first is the mean field parts, and the second is the two-body matrix elements parts resulting from the residue interaction. And thanks to the MSU group, thanks to a series of works done by the MSU group in the 1990s, now we know that the nuclear shell model is a quantum chaotic system, and its eigenstates obey the eigenstate normalization hypothesis, maybe in a weak sense. That is a technical details. So when playing with nuclear shell model, typically one restricts the model space to for example, to the SD shell to reduce the computational load. So also one use the bit representation to record the wave functions. And here here the one state means that the orbital is occupied, and the zero state means that the orbital is unoccupied, and the general wave function is a superposition of these bit strings. And thanks to the bit representation, we can easily translate the bit representation into qubits by just mapping each single particle orbital into a qubit. So we have so for the full SD shell, we have 24 qubits, and for the full PF shell, we have 40 qubits, and then we just play with the qubits. we can divide all the orbitals, or let's say all the qubits, into two parts and work out the bipartite entanglement between them. That will give us the orbital entanglement. And as a special case, when we have only one orbital in part A, and in part B we have the rest of all the orbitals, we will get the reduced density matrix of part A will be given here, very simple forms, and the gamma I is a single orbital occupation numbers, and this will give rise to the single orbital entanglement entropy. And so here, I first studied the entanglement entropy in the ground state of -20 in the SD shell. In other words, we have 4 valence nucleons, and the total number of orbitals, or the qubits, equals to 24. And I just divide these 24 qubits into two parts, and let's say the part A and part B, and label the number of qubits in part A as NA. And for each values of NA, I can generate, in principle, there are many different partitions of the 24 qubits. Actually, this number is quite large. For most values of NA, the possible partitions, the number of possible partitions are around 10 to the 6. So that would mean a quite large computational load. So in order to reduce the computational load, I generate a small number of random samples for the bipartitions for each values of NA. And
Can I ask?
Okay.
Are these numbers of partitions in shell model basis? So these are all possible configurations, or am I missing something? On the y-axis?
The y, no. This is not the partitions in the shell model. I mean, this means that, for example, I have 24 qubits or 24 orbits. I just divide these 24 qubits into two parts, part A and part B. And NA is just a number of qubits in part A. And let's say, for example, let NA equals to 7. Here I show two different partitions, and actually there are 10 to the 6 different partitions. That's a quite larger numbers. And it is computationally expensive, so I just generate a small number of random samples for each NA and do the computation, and then slightly enlarge the number of random samples to see whether these results, to see whether the final results converge or not. Okay, here is the results for the ground state of -20. And the horizontal line is the number of qubits in part A, and the vertical line is the reigning 2 entropy. And each data point in the figure corresponds to a specific number, a specific value of N1 and a specific bipartition. And here I just generate for each value of NA, I generate up to 100 random bipartition samples. And you can see that there's a sizable spread for the data, which does not look good. So a natural choice is to average over different partitions for each NA, for each values of NA. And the results is surprisingly simple, and you can see a very smooth behavior after averaging. So the horizontal line is also the number of qubits in part A, and the vertical line here, not the raw data of the reigning 2 entropy, but the average radiant 2 entropy. And what is most surprising is that these data points can be fitted very well by a simple formula with only two parameters. And for the case of ground state of NU 20, actually the two parameters A and B are approximately equal. So in other words, for the ground state of NU 20, the information behind the scaling behavior of the average radiant 2 entropy can be captured very well by the average single orbital entanglement. I mean, this single orbital entanglement almost determines the scaling behavior of the entanglement entropy. And let's take a close look at the fitting formulas. These fitting formulas, I mean, in the first, when I put it in this form, I just want to make it manifest symmetric between part A and part B. And the second line is some simplification. And I can pick out the volume law scaling explicitly. And the first term is a volume law scaling, and the second term is a small is small numerically, and the last term are not dependent on A. And you can see explicitly that this fitting formula gives rise to the volume law. And actually, this fitting formula was originally proposed to study the scaling of entanglement for the canonical thermal pure quantum states. These are some hypostatic quantum states that aim to replace the canonical ensembles in statistic mechanics. It is still not quite clear to me what's the relation between the canonical thermal pure quantum states and the nuclear shear model states. But nevertheless, their formula works quite well, although their starting point is quite different from the nuclear shear model. And then I extend the analysis to the excited states. So here I show the result for the 100, 200, up to 600 eigen states. And similarly to the ground state, they all obey the volume law, and their data and the data points can be fitted very well by the simple formula. And also, I do the analysis for some for even simpler isotopes, such as oxygen 22. So here, instead of 24 qubits, I have 12 qubits because I only have half of the SD for SD shell. There are only 12 orbitals in the. There are only 12 orbitals, so there are only 12 qubits here. And also, I see the. So in the figure, I show the result for the ground states and also some excited states, and also similarly, I see the volume law scaling. And this is the result for NEO 22 and also ground states. Also for the ground state and the excited states, still the volume law behavior. And this is the results for the PF shell. This is the result for the ground states of the titanium 44, and I also have other results for the FP shell nuclei in my computers, but in general, their behavior are quite similar. They all show the volume law behavior. And after getting these results, a natural question is where they come from. So in principle, there are two possible sources for entanglement generation in nuclear shell model. The first is nuclear forces, explicitly the two-body matrix elements resulting from the residual interactions. And the second is conservation laws, such as angular momentum conservation, priority conservation, isospin conservation. And in general, I mean, in order to have good quantum numbers for nuclear shell model states, one has to do the angular momentum or parity projection, some operation like that in for example the J scheme approach to nuclear shell model, and these projections will also give rise to entanglement. So in order to separate the two contributions, so the first from the nuclear force and the second from the conservation laws, I do the following computation. I turn off the two-body matrix elements and then calculate the scaling between and then calculate the scaling of the entanglement entropy. And here I show the results. The blue line are the physical case where I don't turn off the two-body matrix elements, and the green line and the orange line shows the results where I turn off the two-body matrix elements. So this is a free theory. All the entanglements are generated by conservation laws, such as angular momentum conservation, priority conservation, isospin conservation. And it is surprising to see that the conservation laws actually gives a large proportion of the final entanglement entropy. So here up to 60%. This is a good news. This is a good news for mean field theory approach to entanglement in atomic nuclei. That means even the residual interactions are omitted, one can still get a sizable entanglement by doing angular momentum. Let's say angular momentum projection. I mean, this is a good news for mean field theory.
Sorry, Donbai. The maximum average is that, well, what is the meaning of the maximum average you have here? It is related to the maximum entanglement or something like that?
You mean this value?
Yes, exactly.
For this case, no, because the maximum in the maximum. I mean, this is only the maximum value for the ground state, and for excited state there are even higher values for this peak. I mean, in general, the maximum value should be provided by the page curve. That is for the random state. That is for random states in the Hilbert space, not necessarily eigenstates of the Hamiltonian.
Oh, okay, thanks.
Yeah. I mean, the ground states are not that random, so although it still obeys the volume law. And the last but not least, I want to answer a crucial question. So in the previous slides, I just showed that many eigenstates, actually most eigenstates of the nuclear shell model obeys the volume law. A natural question is, does all the eigenstates of nuclear shell model obeys the volume law? I think the answer is no, because I found some counterexamples in the energy spectrum of neo-20. Here I show the results, the scaling behavior for the for the 14th eigenstate of nu 20. The blue line are the best fit using the previous fitting formulas I showed. And you can see that the fitting is not that good. Then I started the scaling of the first the first few points, and I found that the scaling is like this: the an proportional to an up to a power of 0.3, and this 0.3, this power, although not as small as a typical error law, that is approximately 0.67, but still smaller than a typical volume law, that is around 1. So I think this corresponds to sub-volume scaling. And according to the definition of quantum manifold spheres proposed by Ma, Bollier, and Yang in a PRB paper, the appearance of the sub-volume scaling could mean these states correspond to quantum manifold scars. So I think these states are quantum manifold scars in nuclear shell model. So this is a summary of my talk. I mainly studied the scaling laws of entanglement entropy in nuclear shell model, and I found that most eigenstates covering both the ground and the excited states satisfies the volume law. And I also found that the scaling behavior of the average orbital entanglement entropy can be fitted very well by simple formulas with actually 2 parameters. And in other words, this scaling behavior, the scaling behavior of average orbital entanglement are largely determined by the average single orbital entanglement. And also I found that the conservation laws play an important role in producing orbital entanglement. That is a good news for mean field theory calculations. So you can also study quantum entanglement in mean field theory as long as you consider all the constraints from the conservation laws. And also I found there may be quantum manifold scars obeying sub-volume scaling in the spectrum of nuclear shell model. Okay, that's the end of my talk. Thanks for listening.
Very much. Are there any questions? Dong.
Very nice talk, very interesting. So I was wondering, you're averaging over all possible NA subsets, right?
Yes.
What would happen if, so that includes things that are sort of well separated and disconnected sort of subsets, right? What would happen if instead of averaging over all of them, you only took the minimum entanglement entropy and just plotted it, the minimum entanglement entropy over all subsets of size NA and then plotted that? Do you know what that would look like? Yeah, you can see it from there, I guess.
I don't, I mean, there, so I think the figure will not, so I think the curve will not be that smooth.
Yeah.
There will be some
Jumps.
some up and downs. I also tried, actually I tried to the maximum here. I mean in another privately, still there are some up and downs. Although in this figure, yeah, not for this case. There are some up and downs for the entanglement. The behavior is not that smooth.
Okay, thank you.
When you were talking about your methodology on how you do this, you were talking about using qubits. Were you actually doing these calculations with like quantum computers, or was that just the way that you conceptualized the
doing the calculation in a quantum computer, only in a classical computer. Okay. But this qubit language can also, I mean there are people trying to put the nuclear shell model onto quantum computer, into quantum computers, they actually use a quite similar language by mapping bit strings to qubits, and that's one way to implement the nucleus shell model into quantum computers. And also, it's quite in classical computers, I found calculating entanglement is quite computational expensive. So a natural step is to trying to work out some way to calculate entanglement on quantum computers. That may help when considering the considerable progress in the near future for quantum computers.
Any other questions? Yeah, Joe.
Yeah. So, have you ever tried to modify your two-body interaction in the shell model? I mean, shell model interaction to see the curve will change or not. For example, if you increase the interaction, so you will get more entanglement.
There was some saturation behavior. I mean, when I don't have slides here. When I time the two-body matrix elements, for example, by a factor of 2, there will be some increase, but the results will not be quite different when I time the two-body matrix element by a factor of 10. There is some saturation for the entanglement entropy.
Yeah. And when you do this kind of sampling, do you treat neutrons and protons equally? They say same. You just take them as 20 particles. So,
Yes, I also have the results for the odd mass nucleus, but I don't show them here. I mean, they don't need. I mean, there's no need that the number of protons and number of neutrons should be equal to each other. Because I just do the bipartition for orbitals, not for the protons and the neutrons, but for orbitals.
Anything else?
Sorry, one more. You might have talked about this and I might have missed it, but did you see a difference in entanglement entropy for nuclei with filled shells versus not filled shells? Did you see a difference in entanglement entropy with nuclei that had fully filled shells? You might have said it and I might have missed it, but.
Full shell, yeah.
Because I'm working within the framework of nuclear shell model. I think this is not for the closed shell calculation.
Okay.
Yeah. For the closed shell, I think the better choice is the cup cluster. Maybe.
Like initial methods. Yes. Can you comment on, so you're collaborating with experimentalists here. Can you tell us a little bit about the work you're doing, how you're planning to measure entanglement, right?
Here, this work is not related to entanglement measurement. Although what is quite interesting to me is that the scaling is almost determined by the average single orbital entanglement, and the single orbital entanglement is determined by the single orbital occupation numbers. I found some old literature which talk about how to measure the single orbital occupation number experimentally. So in principle, you can measure the single orbital entanglement experimentally. But for the two orbital entanglement, because in general we have two parameters here, but for the two orbital entanglement, I have think about the question, but it's quite difficult to extract the whole information from experiments, according to my understanding. And if for the project collaborated with Wolfie, I think Wolfie is better
You want to say something? You want to say something? I think he's interested in what?
I mean, I wanted to let everyone know that so Dong is here for a few weeks and he's collaborating with Wolfie. They're trying to measure entanglement, as I understand, in beryllium-6, right? The 2p or correlation.
Okay, may I ask a very naive question?
Okay, well, I was hoping.
Is there a measure, because we are experimentalists, are there measurable signs that this description is better than standard shell model?
What description? The description of entanglement, or?
Well, this description of shell model with entanglement, does it have some measurable quantity that shows this is a better description than standard shell model?
Here, I only studied the entanglement properties of the nucleus shell model. I haven't think about how whether this would lead to some better descriptions based on entanglement. I haven't think about that question by myself, but I see some paper done mainly by Calvin Johnson. He discovered that the entanglement between the proton part and the neutron part are weak. So he's trying to develop some simplification to the to shell model based on his observation that there's a weak entanglement between the proton part and the neutron part, and that may lead to some better description, especially for large model space. Yeah. But that's not my work. That's done by Calvin Johnson.
I would expect that something like long-range properties would be somewhat different because the entanglement goes to infinite distances.
I mean, I know this work of Calvin Johnson, and they specifically were looking at the spectra. So what they were concerned about was that they were trying to decrease the computational size of the problem. So they diagonalize in proton and neutron, or protons and neutrons separately, and then combine them. So the sizes of proton and neutron separately are way smaller than protons and neutrons together, right? The basis state. But the question was, okay, if the protons and neutrons are strongly entangled together, then you can't do this. That wouldn't work well. And they were showing that they are not very strongly entangled, at least in the shell model basis. And that's why you can do it. But I think they only looked at the energy. So I think your point can be quite valid, that the long range observables may not work so well. But these are recent works, so these are interesting questions, certainly. Okay, anything else? And I don't think there's anything on the Zoom. Great, let's thank Dong again. If anyone wants to meet with Dong, so he's going to be here for a few more weeks. You can, so he's in the room number 20, it's one of the 20 something.
The students.
Yes.